Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back. Acids and bases. We're going to compare acid strengths and see why certain molecules are way more acidic than others. We talked about two effects last time. There are a total of 4 that we'd like to talk about. Actually, there should be 5 and the 5th one should be solvent effect. But for right now, let's just talk about 4. One of them is going to be the first one was the element effect. What element the hydrogen is bonded to before it dissociates is key to the acidity of the molecule, right? We also talked about how if the anion, the conjugate base, is more stable, that makes the acid more acidic. And so the element will stabilize the anion if it's more electronegative and make it more acidic, and we saw many examples of that. We also talked about how hybridization plays a role, how sp-CHs are more acidic than sp2-CHs, and that's more acidic than sp3-CH. It's not just for CH, it's for any element that's bonded to a hydrogen. The hybridization affects the acidity a lot. And we saw all the reasons for it. Today we're going to talk about 2 effects, resonance effect and inductive effect. Resonance effect is really very large. Inductive effect has a small effect, but resonance effects can be very large. So let's talk about resonance effect. What is a resonance effect? When you have a high acid dissociate, you are left with an anion. The anion is basically an electron that is a lone pair on some atom. If that lone pair is just sitting on that atom, it's localized. Localized charges are not very happy. But if the molecule can take that charge and pass it on to the rest of the molecule and distribute it and delocalize it, it's a lot more stable. All right? So we will talk about stabilization of the conjugate base via delocalization of pi and lone pair electrons. And we already talked about that very important concept that if you have an acid, note, HA will go to the right more if you have an A minus that is stable. If A minus is stable, equilibrium will shift right, and as a consequence, you will get more and more H plus. So A minus stability is proportional to the acidity. So when we talk about acids and bases, forget about the acid, talk about the conjugate base. Because that's the guy who's going to determine if the equilibrium is going to shift to the right or not. So that's an important concept that's going to be throughout the semester, not just for this acid-base topic. Throughout the semester, you will see consequences for those. Let's look at an example. Here's a carboxylic acid. All of these are OHs, and we're talking about the pKa of this OH coming off. So here, if you talk about the conjugate base of this, as I said before, the A minus stability is the thing that really determines the acidity of HA. So if you talk about the conjugate base, we have to take out the hydrogen as an H plus. Therefore, those electrons are going to go on the oxygen. So here we have a conjugate base that has now 3 lone pairs. And over here, if you take this and give those electrons here, you would have a conjugate base with 3 lone pairs. And here too, you would take off the hydrogen, give those electrons over there, and end up with 3 lone pairs in all cases. So the oxygen itself doesn't seem to be the main factor. There's something else besides the oxygen anion that's making it acidic. Now, having it on an oxygen is definitely a lot better than having it on a carbon, which is why we're not even mentioning the pKs of these, because these are going to be, especially this one, would be pretty high. But the reason why this is so much lower is one, element effect, but in this case the element effect is the same. So there must be another effect in addition to that, all right? And all of them, well, they have a pi bond next to it, and this one doesn't. So you can see this one has a very high pKa, and you know when pKa is up, acidity is low. pKa is low, acidity is up, right? So let's look at this. Why is this so much better than any of these? Well, resonance, and we talked about resonance before, is the delocalization of electrons onto adjacent carbons that have pi orbitals or lone pair orbitals or empty orbitals. So here, this can go over here, but it's got to chase this out, so you can have a O minus and a double bond here. So your minus is now on the oxygen. Over here, we can do the same thing. This lone pair can make a bond here and chase this pi bond to the next carbon. So you have a minus here and a oxygen there. Now those electrons can go around the ring and eventually up there. So this can go down, and well, there's already a hydrogen, 4 bonds. One's got to snap. The weakest one is the pi. So the weakest one snaps and goes over here. And this can go around the ring. We'll just write a few of these. And these are resonance structures. So here's your lone pair. And so because now you have your formal charge would be 4 minus 5 is going to be a negative 1. And so then this is going to go here, and then eventually it's going to go here. Now, that's 3, and we can draw 2 more. So there's actually at least a minimum of 4 resonance structures there. Let's look at this one. This one is going to be just this going over here. And over here, this one's got no place to go. It's a minus sitting there. Localized. So localized charges are bad. That means they're really unhappy. Why is that? Well, we talked about chloride ions and sodium ions. They were very stable. We didn't have problems with stability when we talked about anions like chlorides, sulfates, bromides. But over here we're saying this anion is bad. Why is that? That's because when you talk about inorganic salts, sodium, chloride, bromide, and so on, you're putting them in water. They are only really soluble in water. Water is so polar that it can stabilize those anions really well. And you got an excess of water that can really stabilize it all around. Whereas when you take alcohols, you're in a non-polar environment. Alcohols are neutral. It's like water. pKa of water is 15.7. So and this is just like water. I mean, you know, alcohols are, when you drink them, it just feels pretty neutral, right? So you're going to have this localized charge in a neutral environment. There's no external solvent stabilization like in a water environment. So therefore, organic anions are not very stabilized in a neutral solvent, whereas sodium and chloride and bromide, those are very stabilized in water. Also, we have another factor here. We have inside this molecule electrons being pumped towards the anion, making it even more unstable. So when you have an anion on an atom, it's best to take it away and distribute inside the molecule. You don't want more charge pumped onto that. You're making it much worse. Over here, we only can draw 2 resonance structures. Here, we can keep drawing, more resonance structures. So why is it that even though you have 4 resonance structures, the pKa is about 9.9 and this is about 4.8. So at least 10 to the 5 times more acidic, even though there's only 2, and over here you can have like 4. Why is that? We did say more resonance structure, more stable, right? That's pretty much what we talked about when we talked about stability through resonance. The more resonance structures you have, the more stable they are. But look at what these anions are on. Here it's an oxygen, here it's an oxygen. So that's both very electronegative anions, and so when you have an electronegative atom, they can pull that anion in and stabilize it. So more anions on electronegative atoms, more stable, way more stable than if you have anions on carbon. Carbon's really not interested in an anion. It's pretty happy being neutral. It doesn't want an anion. So therefore these, even though you have a lot of these, they are still not as good as having the anion just purely on oxygen. So that's why this is so much more acidic than this. Well, when you compare this and this, 9.9, 10.5, this is lower because you only have 2 resonance structures possible. One of them is on a carbon. And over here, there's absolutely no resonance. It's localized. In addition, you're having electrons being dumped on the anion. So it's really unhappy. So this just clearly shows you that if you have resonance and your electrons delocalized, that stabilizes the conjugate base. And when you stabilize the conjugate base, then your acidity increases. Let's look at another one here. Another example. We have over here a hydrogen in the middle of 2 carbonyls, and we have a hydrogen at the end. So that's kind of like here, right, next to that. Why is this over here, the Ka is 10 to the minus 9, 10 to the minus 20? So pKa here is a lot lower than here, even though they're both next to carbonyls. What do you think would be the reason? It would only become really clear if we draw the resonance structure out. So let's take out this hydrogen, give those electrons over here, pop out your H+, which is what's making it acidic, and let's draw that anion right here. What are the possibilities for this anion? Well, it's got 2 good friends, oxygen here, oxygen here. And so there you go, you can run in here and do a resonance right here. And, well, it gets tired of that oxygen, it's got options. It can go right next door to this oxygen, knock on over here and say, oops, can I come in and watch TV over here? You got so many options over there for this anion. So this is something that makes that anion so happy. It wants to be more over here than, let's say, something that doesn't have a carbonyl. So lots of resonance structures, and resonance structures that have anions on oxygens are like the best case scenario to stabilize your conjugate base. If you take this one, and I'm going to draw these resonance structures over here. So there's an anion here on carbon here. So the hydrogen gives the electron and dumps it on that carbon. There's only 1 oxygen to go to. You kind of have a fight with your parents, you can go next door to your neighbors. That's about it. You can't really have one neighbor saying, all right, come over, and then they get tired of you. You can run over to the other neighbor. You see, you got a lot more options here. Here you're just stuck with this one neighbor. So not as great. What about this guy? Well, over here, yes, you can have resonance, but the person who accepts you, the carbon here, really doesn't like anions. So they just want to get rid of you. They're like, going to kick you out any minute. Maybe another day. So this is not very happy because carbon ions are not that great, not very stabilized, because as you know, carbon is not electronegative. Carbon is a larger atom. And so this nuclear charge on the surface area is kind of low for that period, the second period. So the anions are not very stabilized. And look at this guy. Well, he's got a fight at home. He's nowhere to go. He's just stuck here. Pretty much there. Miserable as ever. No one to say, okay, well, you can come over here or here. Nobody. So this is the most unhappy anion. And so that's why the pKa is so high, because it doesn't want to go here. Pretty much over here. I hope that's helping drive the point home, right? More resonance structures and more resonance structures that distribute the charge on electronegative atoms, the more stable the conjugate base. The more stable the conjugate base, this goes higher. As a consequence, H plus is going to increase. Therefore, HApKa is going to drop. All right, let's look at this series down here. Well, we're talking about NH dissociation. I know usually you talk about amines as bases, where this lone pair kind of hooks onto an H plus, like in ammonia, like you would have done in Gen Chem. We're talking about the dissociation of this hydrogen. That means this hydrogen leaving as an H plus and leaving that lone pair for the nitrogen. Nitrogen is, after all, electronegative, so it's going to be happy. So this is a reaction. Deprotonation is not resonance because we're breaking that sigma bond there. So let's start with the starting amide. And here you can see this again can go over to this oxygen and get stabilized by that electronegative oxygen right here. And this can then come back and it can get stabilized on this oxygen. So it's got lots of options. The more options you have, the more you can travel and see the world and move around that molecule, the more stable you are. So you can see this is then going to stabilize into this anion over here. So I'm just making the pi into a lone pair and the lone pair into a pi down here. And this pi has to move over here so that you don't have too many bonds on that nitrogen. So over here we can see that is anions on electronegative oxygens and nitrogen. So it's really stable. You want to get this hydrogen off. You can do that with, let's say, potassium hydroxide. It's just quite acidic. Let's say you have over here, this is 18, this is 8.3, more than 1 billion times less acidic than this. Let's see why. Let's take off that hydrogen, give it over here, and you can have a nitrogen here that's an anion. Well, it actually would prefer to be on the more electronegative oxygen. So it will have over here a resonance structure. And this is an amide resonance structure. And this is what happens in your proteins all the time. Your proteins are all amides, which are in resonance, which is what makes them soluble. You can be transported in water, and it can have a very strong backbone for your muscular proteins or all of your proteins. So amide resonance is so key to your physical structure. So you can see that this amide is really stable here. So your anion is not here or here, it's spread through this, but it's mainly on the oxygens and nitrogens and more on the oxygens because they're more electronegative. So that's why this guy is more acidic than this. This is 10 to the 20 times less acidic. So once you let go of that, you're going to have an N minus, and where is it going to go? It's just going to sit on that nitrogen. No resonance, no neighbors, nobody wants it, it's localized, it's stuck. And that can lead to a lot of energy build-up, stress, right? So therefore, that's very unhappy anion when you take off the hydrogen, and so it doesn't want to go there. Therefore, it doesn't want to spit out that hydrogen, therefore it's not acidic. So that's resonance for you, and we can see how more resonance on more electronegative atoms will make a molecule a lot more acidic. All right, let's talk about another effect, inductive effect. What do we mean by inductive effect? Inductive effect is mainly through sigma bonds. Here, you're taking those electrons and moving them through pi bonds. Here, inductive effect, your electrons are where they are for the most part, and your sigma bonds kind of give it a little tug to kind of delocalize it internally. This is also internal, and this is also internal, but this is through pi and lone pair, this is through sigma. That's the main difference, but both of them are delocalizing those, trying to delocalize those electrons internally. Because externally you may be in a nonpolar solvent, so you don't get that stabilization in your environment, so you're trying to do it internally within the molecule. So the more you can take that electron, the charge on that electron, and move it along the bonds inside the molecule and spread it, the more stable your anion is going to be. If your anion is stable, and we said this like a zillion times now, your acid equilibrium will shift forward and spit out more protons, making the A more acidic and the pKa lower. All right. So by definition, a change in electron density along sigma bonds that leads to unequal sharing of electrons. So electron density distribution is the reason for this. Let's look at this. This is acetic acid. You've seen that a million times in Gen Chem. Now you put one chlorine here, the pKa drops by like a couple of points. That means it's like 100 times more acidic. And over here, you put another chlorine, it goes from 2.87 to 1.25. And you put another chlorine, 1.25 to 0.70 trichloroacetic acid. Now, let's see, is this due to resonance? Well, let's draw the anion for all of them. The anion for all of them would be this. They'll all have the same resonance. So the same anion over here, but now you have two chlorines. So do the chlorines participate in the resonance? Let's try that out. Over here, so this anion can go over and cause an resonance over here. It doesn't go to this carbon. Same here, you can go over here, but it doesn't really go into this carbon. So even though the chlorines are right next door, they're not participating in resonance. So we got to go down the list. Is it a charge effect? The charge is the same on all of them. Is it an element effect? The element is the same on all of them, so it's not that. So the next one, is it resonance? The resonance is also the same on all of them. And I'm not going to draw all the resonance structures here. For one thing, I don't have space, and two, I've done it many times over here. So over here, those are all knocked out. So the only other thing that we can think of is inductive effect. Well, we have a chlorine. The chlorine is electronegative, and we know that because it's group 7. It's got 3.5 electronegativity, and carbon's about 2.5. So it's going to pull electrons along the sigma bond. There's no lone pair coming down because there are two hydrogens here. There's no space for that. That's going to then create a delta plus here, which is going to pull these electrons over, and that's going to distribute some of the lone pair electron density into the sigma bond. So the hybridization such that this becomes more electron dense and the lone pairs kind of shrink a little bit, and the sigma bond electron density is just spread through here. So once your electron density is distributed here, that would stabilize the anion to some extent. Again, it's not as good as putting a whole charge on a resonance, but still it's pretty good. It's better than nothing. Here we got two of them doing the same thing. So you're having a tug of war here, and there you go. You're getting three of them here. So it's dropping even more. So that's something that we would see in all the cases where you have a conjugate base that's linked to a electronegative atom somewhere along on the sigma bond. Here is ethanol. It's about 16. It's not at all acidic. But the minute you put 3 chlorine atoms, the pKa drops, which means it's a lot more acidic. And when you put 3 fluorine atoms, also it drops. So what's going on here? Well, in the case of the ethanol atom, there's nothing here to pull the charge in. There's no resonance, and there's no inductive effect. Whereas at least this guy has got 3 chlorine atoms next to it. And so the 3 chlorines kind of pull those electrons to themselves along the sigma bond, which creates a little bit of a positive, which is going to grab these electrons from the neighboring carbon, which is then going to take those electrons from, this is from the conjugate base, from that oxygen and pull it in. So therefore, the electron density on the oxygen diminishes a little teeny bit. So this is, let's say, 13. This is about 1,000 times more acidic because of the chlorines. And the same, fluorines are going to be even more powerful withdrawers than chlorine. Now, let's look at this over here, this series here. They all are bromines, but your pKa is dropping along this series. What's going on? Well, here we have a 3-carbon chain between the carbonyl, the oxygen here, and the bromine. Here we have 2. Here we have 1. Why does that matter? Let's draw the anion and see why. Why is it that it makes such a difference when you have so many in between? So over here, when you have a bromine, your oxygen minus, again, this oxygen minus is not here, but it's 50% here and 50% here, all kind of distributed along this arc here. And this anion has to, well, for this bromine to stabilize that, it's got to pull this in, and that's got to pull this in, that's got to pull this carbon electron in. And so the inductive effect falls off with distance. So that's something to remember. Inductive effect is going to increase as the electronegativity of neighboring atoms increases. Inductive effect is going to fall off with distance. So that's something to remember. So 2 things about inductive effect. It's almost like a tug of war. So you have a guy in the very front, who's big and strong, you can just yank over the whole group. But if the big and strong guy or gal is at the very end, then they have to pull the string, and everybody's got to pull the string, and then it's going to have an effect. So here it's right there. Proximity matters. Distance matters when you're talking about inductive effect. So here's a bromine, and you have an anion right here. It only has to pull through 3 of these bonds to stabilize it. Whereas over here, it's got to pull through 1, 2, 3, 4, 5. So it kind of falls off with distance. Same, this is somewhere in between. So here we have we are this pulls this, and this has to then pull this, and that's got to pull this, and so it's really kind of diminished by the time it gets over here. 4 bonds. Fewer the bonds or the distance, the greater the inductive effect. Let's look over here. They're all alcohols, OH. So we're looking at the hydrogen dissociation. And, well, why is it that certain alcohols are more acidic than others? Here you have a tertiary, secondary, and primary. And then you can have methanol, of course. And then you'll have water. As I said before, inductive effect only has small changes most of the time, like 10 to the 5 times or less on the Ka. Whereas resonance can have huge effects, like 5 or more. For example, this is almost 11 times difference here. Why is it that tertiary alcohols are less acidic than primary? Well, again, looking at the acid is not the way to go. You got to look at the conjugate base. There you go. Let's look at the conjugate base and see why. They're all alcohols, and they all pretty much have the same type of hydrocarbon linked to it. Here we have 2 carbon-carbon bonds, and here we only have 1 carbon-carbon bond attached to this CO. That's the only difference. Other than that, everything is the same. Why does that matter? Just like electronegative groups withdrew electron density through sigma bonds, electropositive groups are things that have carbon, hydrogen that are not really electronegative. These guys actually donate electrons. These are electron donors. So now you have an anion trying to somehow shift that electron density somewhere left, right, up, down, somewhere. It's got too much of it here. And then what do these guys do? Instead of helping, they dump their electron density into that too. So this guy's really, really unhappy. Very, very unhappy. Wow. This guy's only got 2 people dumping in here. This guy's got only 1 person dumping in here. And this guy's got nobody dumping in here. Hydrogens really don't dump electron density into that much. They are polar, but they only have a 1s, whereas these guys have more electrons to dump in. The sigma bonds are polarized in this direction. So that's going to make this even more unhappy. So unstable, low acidity. Stable, higher acidity. Therefore, primary alcohols better than secondary, better than tertiary alcohol. It's the same when we talk about alkanes. Well, they're all alkanes, gasoline. Those are not really acidic. But again, everything's on a relative scale. Even these guys, they want to be stable too. But this anion, that's 53. This is 51. This is 50. And CH3 minus. So here, same thing. This anion wants to kind of pass that electron density somewhere, but nope, other people are actually dumping more into that. So therefore, this is kind of upset. This guy, same here. And this guy is only 1 person dumping. It's not that bad. This guy doesn't have anybody else dumping into it. So you can see that the acidity goes up. So for alkanes, it's the same thing. Tertiary alkanes are the least acidic. But what about basicity? Well, we said Ka goes up, Kb goes down. Acidity goes up, basicity goes down. So for the anions, well, which one do you think would be the best base over here? Obviously this guy. Right? Because it's so unhappy, it's going to grab a proton from anywhere to go over here. So basicity is going to go in this direction. For the anions, basicity would go in this direction. RO minus anions. Same with the RH. RH acidity goes in this direction. Basicity goes in this direction for the anion. And that's true for everything pretty much. All right, so I hope that helped kind of bring things home to you on acidity and basicity and the reason why certain things, molecules are acidic and certain molecules are neutral or even basic. It's a whole range. So in summary, I'd like to talk about the resonance effect and inductive effect and what effect they have on the acidity of the molecule. So here's the definition of kind of the resonance effect. So in future, guys, if there's stuff written on the board and you want to copy it down, the best thing is to go to the very end of the video and then copy it down there. We try to pretty it up before we show it to you at the very end. So the resonance effect is the stabilization of the conjugate base, which is the molecule after the hydrogen comes off of the acid, by delocalization of the pi and lone pair electrons by resonance. This is going to increase the acid strength. The more resonance you have, the higher the acidity. Another thing is the more resonance you have, that puts the anion on electronegative atoms like oxygens or nitrogens. That also increases the acidity of the molecule tremendously. This is a classic example. Here, the anion is delocalized between two oxygen atoms. Here, the anion is delocalized between an oxygen atom and over here, all of these carbon atoms. So there are a lot more resonance structure here because this molecule has a lot more possibilities for resonance due to all of those pi bonds. But still, this molecule is way more acidic than this molecule. That's because the electronegativity of that oxygen really helps to stabilize the anion. Carbons are not electronegative, so they don't really stabilize the anion. And you can see that if you have no stabilization through resonance, you're a very, very unhappy anion. So therefore, the acidity of this molecule is low because it doesn't want to go there. All right. Now, when we talked about acidity, if the acidity increases in this direction, then the basicity increases in the opposite direction. If this is the direction of acidity, then the basicity would be going in the opposite direction. That means this is a very weak, very, very bad or weak base. We don't even consider that a base. Whereas this is a very strong base, almost like sodium hydroxide. Here too, we kind of demonstrate the same idea. Delocalization on oxygens makes this a lot more acidic, and delocalization on multiple oxygens or electronegative atoms is much more stabilizing than delocalization on like fewer or single oxygen. Delocalization on carbon really doesn't help, and localization is like the worst thing for the anion. So this is very basic, and this is not basic compared to this. This is very low basicity. This is high basicity. Same here. More resonance on oxygen, more acidic. Here there's only one oxygen to share the anion, and here there's none. So it's very, very, very basic. This is one of the strongest bases out there. And so that was for resonance. So that has a huge effect. You can see 10 to the 20 here, 10 to the 10 difference, so billions and trillion difference here. When we come to inductive effect, what we're talking about is a change in the electron density of the molecule due to electron withdrawal or donation along the sigma bonds that leads to unequal sharing of electrons between bonds, which in some case can stabilize the anion or in some case can destabilize the anion. If it stabilizes the anion, acid is going to be a lot more acidic, whereas if it destabilizes it, it's going to be less acidic. All right. So if you want to stabilize an anion, you want to spread that anion into the molecule. Here you're spreading through pi and lone pair. Here you're spreading through sigma. That's the main difference between these two effects. They're still both internally spreading the charge, but through different avenues. And the more electronegative groups you have, the more stabilized the conjugate base, and therefore the more acidic the molecule. The more electron withdrawing those groups are. For example, when you have fluorine, it's a lot more acidic than when you have chlorine or bromine or iodine. So therefore, having more electronegative groups pulling that charge over is a lot more stabilizing than having less electronegative groups pulling the charge over. And the distance also is a huge factor, because if you have many carbon atoms in between, the effect kind of falls off with distance. Whereas if it's really close to where the anion is, then it stabilizes a lot better because it has two sigma bonds to pull that charge through. And another important concept is if the acidity is low, then the basicity is high. And so see the same effect over here. For all of this, that is true. Stronger the base, weaker the acid. Ka times Kb is a constant. All right, so we will work some problems and see you next time. Bye.